Last time we have looked into what a neural network is, how it makes predictions, and how we can tell if the model is good or not. Today we'll go through how the learning process works and how we can improve a neural network's predictions. So let's begin. We have a very simple neural network, a perceptron. We made some predictions and computed the cost. Okay, but how can we use the cost to improve the model? Let's think of what we can change about our neural network. If you remember from last time, I said that we can think of W and B as the parameters of this model. For now, let's look only at W. It will make the problem a bit simpler. Let's change its value, maybe make it a bit smaller, and compute the cost again. This time the cost is smaller. Nice. Let's do it again and try to move the value of W around until we are satisfied. If we record our attempts and plot them on a graph, we might see something like random points. On the x-axis we have W, and on the y-axis we have the cost. We can also imagine that we have gone through all the possible W values and we would get the entire cost function with respect to W. Now it should be easier to see what is the best W value for the cost to be the smallest. The only issue is that this can be a challenging problem to solve. If you have some calculus knowledge, you might know that the minimum of a function can be computed when its derivative is 0. But what if we don't know how to do that, or we are not able to do because of some other random things? Well, here comes in handy gradient descent. Let's say we start with a random W, we get the cost by doing feed forward on the neural network, and we look at the slope. If the slope is negative, then we move a bit to the left, and if the slope is positive, then we move a bit to the right. We keep repeating this process until we get into a local minimum. And this is the only drawback of using approximation. We might not get the global minimum, but that is okay. We can do multiple runs and choose the best one. Now, if we also take B into account, we can see that the problem becomes 2D. We can move two parameters around. For our neural network that recognizes cats and dogs, we have 128 by 128 by 3 plus 1 dimensions. But the idea remains the same. We get the slope of the cost at the current parameters and update the weights. The slope will be a vector with the same dimensionality as the number of parameters. And because it is a vector of derivatives, it is usually called a gradient. Now, if we subtract this gradient from our parameters, we should get a model that is better on average. The process of computing the slopes and updating the parameters is called gradient descent. To continue, we will need to look at a bit of math. We need to compute the derivative of the cost with respect to the weights. We will use the chain rule to make this easier. If you don't know what the chain rule is, let me show you a small example. So let's say we have A over B times B over C times C over D. Obviously this would be equal to A over D because we can, remove the B's and the C's. Again, the chain rule is not really specific to the derivatives, but it just is helpful for us here. Okay, so we have to compute dc over dw. We need to find a dc over something and something over dw at least, such that it makes our lives easier. If we look at the neural network design, we can see a couple of things that we can try to use. What about z or a? Also, take a look at the formula for c, z, and a. I would say that using a makes sense. dc over dA is pretty easy to compute. dA over dw, on the other hand, seems a bit more complicated. So maybe we can split that even more. How about using dz over there? Like dA over dz seems scary, but we use the sigmoid activation. And if we Google search what the derivative of that is, it looks really simple. It is just s multiplied with 1 minus s. Nice. And how about dz over dw? Well, that is just a linear function, which should be pretty straightforward. It is going to be just the previous a. And we have the same thing for b. We just replace, w's with b's. Now we are prepared to write some code that will allow us to make the neural network actually learn. So let's get right into it. Alright, so we have to start with a small update on the neural network data structure. First of all, we need to add, just for convenience sake, let's add a0, which is going to be the input. Right, and for the input, the input size is basically this, right? So we store the input as a0. Then we also store a1, which is the output of the multiplication, which is going to be just a single float. We can do one element, but since it's only one, we can also keep it like this. And we also need z1, right? And to make things maybe a bit more similar, we can call this thing w1 and b1, even though we need to change it in some places. So w1, right, b1. I think these are all the changes we need to make. Yeah, so the reason why we need these is because in the formulas it was easier to compute each one individually for the gradient. So that's what we are gonna do next. So we are gonna do nn gradient, and the other thing here is, instead of doing a const, but I mean let's do it afterwards, we'll have the neural network nn, which we want to compute the gradient for, right? And I think we want the output, so the real output, y hat, for example, and a neural network for the gradient. So in this data structure, we'll store the modifications we need to make to w1 and b1, right? So these are going to be the important fields from the gradient. Okay, but to have all the information, we need to also store it here. So first of all, let's do a mem copy into a0 of x. So we copy the input vector, right? And the number of things we need to copy is like image width times image height channels. I think we also need what, the size of float. Basically, we just need to copy all of this stuff into a0. Then after we compute z, I guess z comes first, but yeah, whatever. z1 is gonna be z, and a1 is gonna be y. But I mean, these are just doesn't really matter. Let me just do it like this. Okay, and here we need to return a1. Okay, so now we also store the intermediate steps in our data structure, which is going to be kind of useful here. So yeah, from the formula, we want to compute the cost derived by dw in this thing. So it's going to be the final cost, which I mean we can compute easily by subtracting from a1 the hat, but yeah, I guess it's gonna be the derivative anyway, it doesn't matter. So we have the derivative of the cost with respect to, it's w1 is the only one that we have right now. We'll add another one later, but for now we have only one of them. So if we take a look at the formula, it was dc over dA, right? And the dA is gonna be the dA1 then multiply with the zy 1 over dA1. Let me just, and multiply with it's yeah, over dz, and dz1 over the w1. So, if you think about it, this thing would reduce with this and this with this. Okay, so now we can compute each one individually and then multiply them together. So that's the goal here. So dc, yeah, so I mean our cost function, we don't have one yet, but it's gonna be the mean squared error, right? So that's what we want to use. Okay, so let's say dc dA1 should be 2 multiplied with dA1 minus y hat, and this is nn. So yeah, I mean, if you remember from the formulas, for the mean squared error, we get this derivative, right? So it's easy to calculate, basically. Okay, then we have another one, dA1 dz1, and this one is the sigmoid, right? So basically from here we can see that a1 is the sigmoid of this thing, and like from the formula of the derivative of sigmoid, this thing is just gonna be dA1 multiplied with dA1 1 minus dA1, or I guess it should be sigmoid of that value. So I guess we can actually try that. So it's gonna be sigmoid of dA1 and I guess dA1 is NNA1, right? So we get that, and the last thing is gonna be to compute the derivative of this thing of z1 with respect to w1, which is from the dot product. It's gonna be basically x, right? So the previous how do you call it, the previous input or activation, right? So it's gonna be a0, and I think that should be everything here. So float dz1 dw1 is gonna be just a0. Well, actually we have multiple a0s, and that, I guess, it makes sense because we want one derivative for each weight, and we have this many weights. So let's actually do a for loop over this thing is equal to 0, I is less than this thing, right? And here we choose the ith one, right? And now we can say maybe gradient w1i is the multiplication of all of them. So multiply with dz1 dw1. well, I mean, this function should return void. So we set this gradient, and finally, if we want to compute the gradient for dB, which is the bias, we just need to replace this with a B. And sure, there are other ways as well, like for example, what if we kept the bias inside of the weights? Like what if this was a 1 plus, when we had a better matrix, but whatever, it's more intuitive like this, I guess. So in here we just need to change the last thing, and since it's only one, we can skip the for loop. Okay, so for this thing, which is interesting, it's gonna be 1, right? If we do the derivative of this thing by b, it's gonna be 1, because it's gonna be something plus b. So it's gonna be 1, and that means, see, and even here, like a0 would be 1 for that value, right? I mean, I'm a bit tempted to just add another one here and make it 1, but yeah, let's leave it like this. So gradient b1 is gonna be this. Right, so this is how our gradient will look like. Now I guess we can also do the backward function, and the purpose of backward, so backward is to only apply the gradient. So let's say like learning rate. Usually this is done by an optimizer, right, in PyTorch and so on. But the idea here is, let's copy paste this because it's going to be useful. Well, I mean, this part. Learning rate. So yeah, basically we use the gradient to update, well, by update I mean subtract from the current weights, we subtract the gradient, and yeah, that's what we need. And let's say that the last thing that we need is the training function, but I was just thinking, well, we could also use something similar to compute true positive that computes the loss, because we might want to see the loss while we train, so that's useful. All right, so here let's say we have loss, which is gonna be float, and then loss plus equal, and then loss y and y hat. Okay, we, whoa, what? Oh, it's gonna be float. So yeah, we can define it separately. It's gonna make more sense, I would say. So let's do it here. Let's see, we have a float y and float y hat, and we just do the mean squared error. Like this. Right. So now we also have this little function that gives us the loss. I mean, you know, we can plot it, but we are just gonna print it. So let's do like a learn function, I guess. We're gonna get the neural network. Now sure, would be cool to have separate train and test datasets, but I mean, you know, let's just see if we are able to improve even on the train set. Like, would be interesting to see, like, yeah. And another thing is, since we have split our train into cats and dogs, we can also pass in the true labels which we would need. So let's say y hat, right? Yeah, I mean, ideally you would have an array and they would be shuffled around, but works too. I don't see a problem with this. Okay, so let's define another. Oh, I already have train count, but I want, yeah, I think it's enough. So we need another for loop again. It's pretty standard at this point. There's a train count and the usual loop for this stuff, but I guess it's pretty similar to compute loss and all of that. First we feed forward the thing, then we need to do gradient descent. So we need to call to this thing gradient descent, but here we have nn, that's great. We just need an extra variable for the gradient, so that's the only thing. I'm gonna call it grad I. You'll see why in a second. So this gradient I is gonna be the gradient for this training example, for the ith one, and we kind of want to combine all of them first and then apply the gradient. I mean, we can do backward here and we can try to compare what would happen. Well, this should be like this. Alright, so we can also do this thing, which really makes everything look really small. And we can compare it. So I was thinking to compute the average over all the examples and then do backward, but maybe this will work. So in here I'm gonna do I'm gonna compute the, let's say, accuracy before we train and after we are gonna train. So let's do, let's say, 10 steps of training. So it's learn we pass in the neural network, we do cat train, and when it's cat, I think I said it's 1. Well, let me just define cat label. So this would be like epochs, and instead of 1.0, I'm gonna use cat label. All right, and let me also do learning rate 0.1. All right, so we do learn on both training sets for like 10 times. And then I guess we can do cat loss. We can compute the loss on both of them. Right, and then float loss is gonna be the average, let's say. And then sure, fair enough, let's say loss is gonna be just loss. Make and run main. Well, it's sad, it got worse, but we can see, well, I mean, after it got 50, it started to drop, right? So maybe if we train it more, or if we play around a bit with the training parameters. When I tested this thing earlier, like using a bigger learning rate, started to do better. So here, for example, it got a bit better. But yeah, I think we just need to run it more. So 100. But I mean, I would say that this is quite obvious it's gonna happen because it's a pretty small neural network. But see, after 100 epochs, it actually got quite better. Well, I mean, I'm gonna try with 1000, but it's gonna take a while, so maybe I can just speed run through this one. But yeah, I mean, right now we only have a single perceptron, and we can add more of them. Even in a single linear layer, we can have more, and then let's say, oh shit, it overfit on it. I mean, I maybe should stop once the loss gets to a certain value, but yeah, damn. Yeah, like when I was testing, I guess I did something wrong maybe while testing, and I didn't get it to overfit on the training data, so that's why I didn't think. Yeah, let me just, if loss smaller or equal than 1, break. But pretty sure that if the loss is 0, then the accuracy is 100%. So maybe that's a reason to use test data. So we can say here offset, right? And for example, we can have yeah, it gets accuracy of 1, so 100%. It's pretty neat. Yeah, but for this one I need to change a lot more. Let's just say cat test, dog test, and we can maybe do something like this. Right? And this way we are gonna get the predictions on the test set. So maybe it's gonna be, oh shit, segmentation fault. Yeah, no idea why, but you'll see right now I don't know why it hates the dog 100 image. So I think I'm just gonna try to skip it, like do here +1. Maybe this would fix it. It's like so random. It's okay. So it anyway. Let's say dog is gonna be from 0. It doesn't really matter. Let's just use new cats in the test set. So yeah. Okay, I guess. Wow, it was already pretty good. So let's see if it's gonna get better. Okay, so yeah, I mean it. Whatever. So this model actually is pretty good. Yeah, during my testing it wasn't getting better, or I guess that much better. So I wanted to use it as a reason of adding more layers and everything, which I mean we can still do. Maybe yeah, I mean this is overfitting obviously, right? Because yeah, we could use more examples. Maybe this will make it, but it's gonna crash again on that dog image. Not really sure why it's not able to load those images, but now it can. What the fuck? Yeah, I mean it has like some stupid issue with loading that image for some reason. So it is what it is. But if we are gonna use 1000 images, it's gonna be extremely slow. Like it's gonna take a while, right? And yeah, I guess maybe I like this. The loss seems to be going down, like overall, if you look like at the average. But yeah, this is gonna be extremely slow. So yeah, anyway, I'll just move it to only 10 epochs. And I'll just make like a checkpoint. Let's remove the stuff for, let's say, backprop. Right, so we did backpropagation for a single, like this really simple neural network. And in the next part, like after the explanation, we are gonna do multiple layers and even multiple like neurons in a single layer. So yeah, let's see how that goes. Congrats for making it this far. For now we have learned how to implement a neural network from scratch in C, and then we looked into how to actually train it using gradient descent. The issue is that my model is pretty trash. It only has a single neuron. So let's try to change that. I will add more neurons in the first layer, and how about adding an extra hidden layer between the input and the output? That would be cool, but we need to go back to gradient descent and dive a bit more deep into the math. Working with a single layer is pretty easy, even if you add multiple neurons. The challenge appears when we make our network deeper. That is because deeper layers will not only depend on the input and the output, but also on the other layers activations as well. Let's see what changes. Since the new layer is the last one, it will stay the same. When we do backpropagation, it will only look at the outputs. But what about our first layer? It also looks at the hidden layer. Well, let's try to use the same formula and see what happens. DC over dw, but this time I will add a prime whenever we refer to the new layer, so it's gonna be dw prime. Well, let's use the same chain rule as before. dc over dA prime, multiply with dA prime over dz prime, and multiply with dz prime over dw prime. Wait, isn't this the same thing? Whoa, slow down there, buckaroo. This time the A is different. It is no longer the full output. So we can no longer compute that easily dc over dA. But dA now is the output of the previous layer. And we have no idea how to compute the derivative. Or do we? What if we go to our last layer and instead of doing the derivative with respect to W, we do it with respect to the input, or A prime? It looks like the input is the same thing that was giving us trouble before. So we get the same thing, dc over dA prime. What if we do the same chain rule like the first time? Well, we get back dc over dA, multiply with dA over dz, multiply with dz over dA prime. So the same formula, but we replace w with A prime. Again, we know how to compute all of these. So we can just go ahead and replace that pesky dc over dA prime with this instead. So we would get back a humongous formula like dc over dA, multiply with dA over dz, dz over dA prime over dz prime, and dz prime over dw prime. And this is the formula for updating a deeper layer. I know it's a lot of math, but I hope it was kind of intuitive. For now, let's just get into the code and modify everything to work with multiple layers, and let's add backpropagation to it. Okay, so let's try to add more layers and make the model, like the neural network, larger. So let's add another define, hidden size, for example. Let's make it 128. So what we need to do is change our W1 to be hidden size neurons. So we want it to be like a matrix now, a 2D array. And the reason is we need one of these vectors for each hidden parameter. Yeah, like that's the only thing. And again, you can see that bias is also going to have the same size. So it actually, yeah, could be like 1 plus, but I'm still going to keep it like this. Okay, and afterwards, we need W2, which is going to be just a single vector. So W2 and B2 are going to be the perceptron that we had before. So that's what we can think about it. Right, so now, yeah, I mean, since we have hidden size neurons in the first layer, we have to use this notation. And then we have Z2 and A2. And again, here, our first layer is actually gonna have, wait a second, is actually gonna have hidden size outputs. Right, so we have more, we have one output for each neuron basically. So, and this should be A2. Okay, so initializing, we need to change this. We need to change the forward function, the gradient, and I mean the backward, it's just because we don't have vector math operations. I think even no, it's enough. So yeah, because we don't have vector math operations, you know, we have to change more stuff. So yeah, anyways, let's do another for loop here. So j plus plus, and we can say ji. Well, it's gonna make our lives easier if we go like this. Okay, anyway. So we initialize these two values and we need to initialize these two. So let's just take the for loop. Yeah, I mean, initializing the second layer is the same as the original one. Okay. So yeah, things are a bit more interesting now. So here we need multiplication between matrix and vector, actually. So let's have something like void mul matrix vector. So maybe const float is gonna be a pointer to the matrix and a pointer to the vec. And let's think about it. The result of this thing is gonna be a vec also, right? So, but I mean, doesn't matter. Okay. I meant it's a float, but you know what I mean. Okay, so now we have to iterate over the rows, I guess. And then we can say result I is gonna be dot product between matrix plus I times calls axis, and n should be, I think, the number of rows. I guess it doesn't really matter, it could be, yeah, number of rows or number of calls. I think it's a number of columns because it's the size of axis, more or less. Yeah, it's gonna be the size of axis. Yeah, whatever. But even then, maybe should have moved this thing at the end. Yeah, I think I want to do it like this. I think it's gonna make the math operations easier. Whatever. So yeah, like if you think about it, matrix multiplied with a vector, you do dot product between the rows of the matrix and the vector each time. So that's how you do matrix vector multiplication. Like that's more important than if it works or not in C. Anyway, so for the forward, right, we need to do this multiplication. And we can just take this thing out, right? We would need the output, which could be z1, right? And let's say we're gonna keep this as a number of columns and hidden size as the number of rows. And sure, even though w1 is like a 2D array, we can reinterpret it as a 1D array. Because if you think about it, I mean, this one is still just a chunk, but it has a different meaning for us. But yeah, whatever. So then we need to add b1, and the b1 is also a vec. So I guess we can have another function. Add the vec. We could also have float pointer result. So yeah, we could just result I is equal to x is I plus y is I, right? And maybe it's add the vex. So then add vex. Let's say we use, I guess we could use z1 and b1, put the result back into z1, and obviously n is gonna be this huge thing. Okay, so now we have z1, and yeah, I guess sigmoid we cannot really, we need a for loop. Y plus plus, and for a1 we could just do sigmoid like this. Like a map function would be nice, but we don't have one. Anyway, so yeah, we did a forward through the first layer, and now we need to do a forward through the second one. So let's see. We have z2, which is gonna be like dot product. The first thing from the dot product obviously is the previous activation, a1, and here is the weights, so w2. But the size of this one is hidden size instead of the image size, so that's one thing. And then the second activation is just sigmoid z2. So again, like the second layer is just like the first one from the previous part, which I mean makes me think that we can keep this thing and just rename everything with A2 instead of A1, right? And I think that's what I'm gonna do, because if you think about it, we can just replace everything with 2's, and it's gonna stay the same, except the size of the array is gonna be hidden size. But this thing is gonna be A2, this also A2, right? Here is gonna be A1, which is the previous layer, right? Previous layer. But here it's W2, all right? And we just increment everything by 1. This is gonna be B2, right? So that's how we get the gradient for our like the first layer. But yeah, the second layer in the list is gonna be more interesting, because we don't have a straightforward way of computing this derivative. Like this one, dA1, dZ1 stays the same, like here, nothing really changes about it, so we can just copy paste it, I guess. It's just the previous, well, I mean, it's gonna be in a for loop. So I guess everything from this part is gonna be in a for loop. Right, because we have multiple perceptrons, basically. So this part is easy to compute. And even this one should be easy, because it's just the previous layer. But again, we are gonna need another for loop for that one. So yes, let's call this thing J. And maybe to not be annoying, we should call this thing I, and this one J also. Like, let's keep I for the hidden size and J for the image size or something. We could have done it in the other way, but like the J for the hidden size and I, but whatever, doesn't really matter if you think about it. But yeah, so here again we need activation from the previous layer, which is A0 or the input, and the gradient is gonna be similar. So gradient of I and J should be Ji though, yeah. Ji is gonna be like this. But again, we don't have a DCDA one yet. We'll get it though. Let me just copy the formula too. Okay. So that's also one, but we still need this DCDA. And I guess how we can compute it is actually by looking at this thing. All right, so let's take a look at this. I mean, we already made I guess, you know, I did the formula, but if we replace in here, let me do another line like that. If we replace W with A, what would we get here? Well, it's like this over something multiplied with something over the A1. Right. Right, so what if here we do the A2, then we multiply with the A2 over dz2, I guess, and then dz2 over dA1. That's my idea for this value. Right, so then we can just replace everything from here with this, and in the end it's gonna you know, cancel out. But it's easier to see it like this. Let me just copy it like that. DC DA2, right? So this one we already have. So maybe we can move it in the front. So we already have it. And even this one we already have it. Right, we have both of them. The only one that's missing is dz2 over dA1. And I guess this one should be pretty simple. So if we take a look at how z2 is computed, is the dot product of this thing. So it's basically this multiplied with this. So if you derive with this thing, you should be left with w2. So yeah, I guess this thing should be w2. So if we do float dcda1, it should be dc dA2 multiplied with dA2 dz multiplied with the weights 2. But I think weights 2 is vec, so we need I. And this should be the entire gradient. Like this was the hardest part, getting the back propagation to work, because we needed this term that depends, like we basically need a cost, but we need to derive the cost with a layer that's in the middle of nowhere, right? So how does the cost depend on this layer? Because we have another layers in front of it and behind it. So that's the hardest part, figuring out how to use the chain rule to make it like, okay, we know this term, we know this one, and this is easy to get from this formula. So like how to link all the layers together. Anyway, let's look at the backward now. So we'll need like the second layer works like this, right? But again over the hidden size. And I guess the first layer works over the hidden size as well, but it also works over J. Something like this, right? And I think, strangely enough, these are all the errors that we had, right? So the learn process doesn't change, it stays the same. We do forward, we compute the gradient, and then we do backward. So we make a prediction, we compute the error of that prediction and how we need to change the weights, and then we apply that change. And I mean, training is just running the same thing multiple times until we get some good results. So let's see. I mean, obviously that's supposed to happen. Again at 192. Well, that's awkward. I guess the problem is that we allocate everything on the stack and yeah, maybe it's kind of too big. Let's do less example and everything just to see if it works first. Okay, so again it failed. And it's annoying, Valgrind is so slow on loading images. 206. Oh, so in advex, interesting. So at the line 44, I mean, yeah, obviously it's line 44, but why though? That's like a good question. Well, I guess it's because the size should be hidden size. I guess when I copy pasted stuff, I forgot to change it. Okay, yeah, so does something, but we need more images, let's say. Sadly. So maybe more images. Increasing the hidden size would be nice. But yeah, I don't know how to increase the stack size. Oh shit. I mean, that's kind of amazing though. Maybe like this thing is too big. Oh. Yeah, like that's the only reason I can think of. Whoa, what the fuck? Okay, now that's is weird. Right. Anyway, let's make the learning rate a bit larger though. And more epochs maybe. And more training data would be better, but let's just see it over fit. Doesn't though. It kind of did maybe, so 90%, but we have like what, 10 images, so it's not that interesting. But yeah, I mean, I'm surprised that the first, like the original one, actually worked that well with a single perceptron. But I mean, it was like overfitting probably. But I still think this is a great way to understand like the how PyTorch works, for example, right? I mean, even though it's an extremely small subset of what PyTorch does, because this what has only linear layers and they don't even work properly. I mean, obviously they work because it's only one way to make linear layers work, and that's dot product and matrix multiplications. But you get the point. The initialization, again, in PyTorch we have like a lot of ways you can initialize the parameters, different losses as well. Like it's there are even better losses that you can use for classification. Like this is a decent one, L2, but cross entropy, for example, or all of that good stuff. Feed forward, I mean, it's dependent on what architecture you use, so it's not that relevant. Then the gradient as well, it depends a lot on what things you use here, on what loss function you have, what activation is you use, so it really depends. But also backward, I think it depends on the optimizer, right? Like how it approximates the gradient or stuff. I'm not even sure how all the optimizers work, but like this, like gradient descent is the easiest one to understand in my opinion, right? Because it's the most intuitive one. You look at the slope at the current position and you go towards the minimum. You don't worry about anything else. Then the training loop really looks similar to PyTorch, am I right? Like we have the forward, get the gradient, and then we do backward. So yeah. Oh, I mean it got stuck at 50%. So maybe this is where my idea of getting the gradient and doing the average. So let's say for 0, let's say j is equal to 0. Let's say j should be smaller than this thing. So I want gradient dot w1 ji increases with the same thing, plus equal right? And then we have, I guess I can use the same thing. W2, and then we have B2. And here we need to do division by train count, for example. I don't know how that didn't work, but it is what it is. So division by train count. So that's the gradient updated. And instead of doing backward here, we're gonna do it here. Let's see if that has any impact on training. Oh shit. I mean, let's not be stupid. Let's only load one image. One image should be enough to make it crash. So it's at 160. I mean, for sure it should be something related to this, but what exactly? Like, I mean, let's just say this is equal to 0. Yeah, so I guess we got to that point where the stack is, I have no idea why the fuck that happens. But it's like, all of this is allocated on the stack, so that is kind of limited, which is pretty cool because if you allocate everything on the stack, it's basically we don't even use the heap or like memory, which is would be a nice clickbait, like doing machine learning without needing memory, whatever that means. But I guess it wasn't any, it was just that the hidden size was too large. So if we want to do it properly, we should probably allocate all of these on the heap when we do that. But yeah, I mean, honestly, I'm a bit surprised that the deeper network worked like worse. But yeah, I mean, no, pretty funny though that it worked a bit worse. So let me just go back to doing the gradient normally, because I don't think it improves anything. And this way of doing it looked a bit cooler. But yeah. Yeah, I mean, still works as a proof of concept, not to be able to learn how all of this work under the hood. So yeah, I mean, still pretty happy with the results, I guess. Yeah, it's only trash that in it's C, and sometimes it works, sometimes it doesn't. So especially this part right here, like it's so random that it doesn't work on like that image of dogs. I have no idea why, but that's C for you. And I mean, if we would do it properly, like not rush for like a tutorial, sure, I think the better way of doing this instead of global variable is to allocate them. And yeah, even this neural network, allocate all the layers with malloc, so you can have any size. Because if you have 2D arrays like this, I think it's limited to something like this one is 16 and this one is huge, but yeah, it's like limited after some certain size. And malloc, I guess you can malloc how much you want, so that's the reason. But enough about C. Yeah, I mean, the loss kind of decreases, right? Even for this deeper network, so that's good. So yeah, I mean, the this would be all for the implementation. I think there's really nothing else left to do that's interesting for the code. So yeah, let's resume back to whatever I was doing. So yeah, see you. Alright, so we made it through. We went over how to implement neural networks from scratch and how to make them learn. Sure, this is not perfect, but it's meant to serve as an intuitive example rather than production use. So hopefully when you will use PyTorch or even implement your own from scratch version, you will have a better understanding of what happens. And this was only a small part of what deep learning has to offer. There are a lot more neural network types, activation function, cost functions, and even learning algorithms. But linear layers, sigmoid, and backpropagation are what I would consider fundamental for deep learning. I hope that you found this series useful, and don't forget to subscribe if you want to see more content like this. See you in the next one.